Today we're going to go through the theory of production. This is a topic in economics class, and as we go through it, we're going to follow the following framework. We're going to be looking at the problems, what we should keep in mind, the prerequisites if there are any, and go through the explanation on how to solve those problems. So the first thing that I'd like us to look at is just how the questions are set and how the problem looks like. So under the theory of production, there is a subtopic known as consumer utility analysis, which essentially deals with consumer behavior. If we can look at these two images here, these are questions dealing with consumer behavior. And if we just take a closer look, you'll see they're talking about utility. Utility. That's a keyword when you're looking at consumer utility analysis. So that's one of the things that I'm noting here that you should keep in mind. It's one of the keywords that can fall under this particular topic. But anyway, I just want us to zoom into the actual explanation of the question that we're going to solve. So let's have a look at this question. So we're going to read through. A consumer's utility function is of the form mu is equals to that. The price per unit of Z is Ksh 20, and the price per unit of W is Ksh 15. The consumer has Ksh 500 to spend on Z and W. Determine the number of units of both commodities that the consumer should buy so as to maximize his utility. So you can see here the key thing that we're looking at is something known as utility. So this is a key word that you should be aware of when you're solving such question. Utility. Anytime you see the word utility, it's often accompanied by the word maximize. As you can see as well, in this particular, at the end of the question, it says, determine the number of units of both commodities that the consumer should buy so as to maximize his utility. So we have the word maximize here as well. So in most cases, when you're looking at a question dealing with utility, will often be accompanied by the word maximize. So those are some of the keywords that you should be looking out for. The word utility, you should know what it means, and as well as what it means when we say maximize utility. So if you're not aware, the word utility is essentially the satisfaction derived from consuming a product or service. That is why we're dealing with something known as consumer behavior. So we're looking at how satisfied are they when they're consuming a product or service. And we're trying to maximize their utility, because most of the time that a consumer is dealing with, they're out buying a product at a shop. They're choosing from different options, and essentially they're trying to maximize the satisfaction that they get from choosing those different products. So that's why they're trying to maximize that satisfaction. Now, mathematically speaking, when you're maximizing utility, you're essentially differentiating. You're seeking to optimize, and what is going to happen is that you're going to have to differentiate a function. So what function are you going to have to differentiate? The function that you've been given here, the utility function that you've been given here. However, we need to keep in mind that the consumer is often limited to. The consumer faces a constraint. So there's always a constraint function that the consumer has to deal with. So in this particular case, we're being told that the price per unit of Z is Ksh 20 and the price per unit of W is Ksh 15. The consumer has Ksh 500 to spend. That's their constraint. That is what they are limited to. However, we need to come up with those two functions first and combine them before we maximize, before we differentiate. So we're going to go through that and see how that is done in this particular case. So first of all, let's just identify what we've been given here. We've just observed that we have a utility function that is already stipulated as U is equals to 10 Z power a half W power a half. And we do have to formulate a constraint function. In this particular case, we formulate the constraint function based on the information that we've just been given by reading what we've been told. In this particular case, they are telling us that the consumer has 500. That's our limitation. That's our budget. 500 to spend on Z and W. So that means 500 must be equal to something. That is the price of Z, that is 20Z plus the price per unit of W, that is 15 for each unit of W. So this is our utility function and this is our constraint function. Constraint. Now in order to solve this question, determine the number of units. The specific question is actually asking us to determine the number of units, the number of units, that is for each Z and W. So in essence, we are required to solve for the actual unit of Z and W for this question. And to do that involves a series of steps that we shall begin to look at right now. The first step I'm going to describe as step 1. I'm going to describe as equate the constraint function to 0. Remember, we've just identified our constraint function here. This is our constraint function that we now wish to equate to 0. We wish to equate the constraint function to 0. Now, how we go about in equating the constraint function to 0 is a bit interesting. When we look at our function, I want us to note that we have our budget, and on the other side of the equation, we have our unknown figures. So we have 500 is equals to 20Z plus 15W. When we're equating the constraint function to 0, it's important to realize that what we move to the other side of the equation are the unknowns. We move our unknown values. This and this is what moves to the other side of the equation. So what will that look like in our case? We're going to have the new equation be 500. When we move positive values to another side of the equation, that turns into a negative. So we're going to have 500 minus 20Z minus 15W, and we're going to say that is equals to 0. So it's very important to note here that what we are moving is the unknown values to the other side. We are not moving the budget. We are not moving this constant figure to the other side. It is the unknowns that we move to the other side. Then we're going to move to the next step. And the next step, I'm going to describe it as step 2. I'm going to describe it as introduce the lambda function, or rather introduce lambda. We're going to introduce lambda. Hopefully we know how you represent lambda. That's how you represent lambda in an equation. And how do we introduce it? We introduce lambda by multiplying it with the constraint function that we've just established in the previous step. So we're going to take the constraint function as we've determined it up here, which is 500 minus 20Z minus 15W. And we're going to multiply this with a lambda function, with a lambda. So when we open up the brackets, what does that become? We will have 500 lambda minus 20Z lambda minus 15W lambda. So that's our next step. We have introduced lambda into the equation. We're going to go to our third step. And for our third step, I am going to say step 3. We're going to create the augmented function. In other situations, this can also be described as the objective function, but I prefer to call it the augmented function. So step 3, we're going to create the augmented function. If you understand what the word augment means, then you know what we're trying to do here. In essence, to augment something simply means you combine. And when you're combining, what exactly are we combining? We need to combine these two equations that we've just come up with here. This lambda function and this constraint function that we had equated to 0. We need to take those two and create something known as the augmented function. We shall call it A is equals 2. When you are combining, we are combining not just the ones that we're combining is actually, just made a mistake there. It is the final constraint function that has been multiplied by lambda and the original utility function, this u. So we're taking this u and this one that we've just multiplied by lambda to come up with the augmented objective function. So what will that look like? We now have u, no need to state the u. We now have 10z to power a half w to power a half, and we're going to take that and sum this right after it. Now how will that look like? That will be 500 lambda minus 20 z lambda minus 15 w lambda. Once we've done that, we've created the augmented function, which we're calling a. We're going to move on to the next step. Now recall earlier that I was telling you that we need to differentiate what we are doing. So what do we need to differentiate exactly? What we're differentiating is what we've just come up with, the augmented function. So our next step is carry out differentiation. Now our particular equation is an equation that deals with several unknowns. When you're dealing with a question with several unknowns, we normally carry out a differentiation method known as partial differentiation. So our next step is carrying out differentiation, and specifically partial differentiation. Partial differentiation because we're dealing with a function that has multiple unknowns. Partial differentiation means you need to differentiate the equation several times, or rather in respect to each unknown. And since we're differentiating the first time, this is normally described as the first order condition. So we're differentiating the first time, FOC standing for first order condition. So under the first order condition, what condition are we describing? Under first order condition, differentiating in respect to each unknown, that is z, w, and lambda. We have three unknowns. The differentiated function for az, differentiated function in respect to z, in respect to w, and in respect to lambda must all be equal to 0. That is the condition that we are referring to here. That is our first order condition, that each of the differentiated functions must equate to 0. So how do you go about doing that? We're just going to see what we're going to do here. For the first function, az, we represent that as a dA dz, meaning we're differentiating the first function, az. We're differentiating this augmented function in respect to the unknown z. So differentiating this function in respect to z alone. In this particular case, when you're differentiating something in respect to one particular unknown, you're normally required to just ignore where there is no that unknown. So I look at this function, only focus on where there is a z. In this particular case, I can see z in two places. I can see z in this particular case, I can see z here, and I can also see z here. So I'm going to focus on that first, these two particular areas, when I'm doing the augmented function in respect to z, differentiating in respect to z. So how will my solution look like? Keep in mind that this particular part of the equation are two unknowns being multiplied by each other. So we need to pay attention to how the differentiation will occur here. So, but under normal circumstances, when you're differentiating, you take the power, multiply by the number in front of the unknown, then subtract 1 from the power. So how will that look like in this case? I'm taking a half multiplied by 10. So I'm taking 1 over 2, multiply that by 10. That is 5. I have 5z, then I subtract 1 from the power. So that means I take the power, which is a half, 1 over 2, and I subtract 1 from 1 over 2. That will give me a negative 0.5. I'll write my solution in fractions. So I'll just write 5z to power negative a half. Next, I'll move to the w. Or rather, when you're differentiating a function where it's been multiplied by another unknown, then the unknown that accompanies it remains the same. So the w remains with a positive a half. There is no z here, so I choose to ignore that. Is there a z here? Yes, there is. I differentiate in the same manner. I take the power here. The power here is 1. even though we cannot see it. It's a 1 multiplied by the 20. So the sign remains minus 20. The z is to power 1. I subtract 1 from that power. So that's 1 minus 1 is 0. A number to power 0 is 1. I'll repeat that. A number to power, is that the case? I am taking, say for example, 5. I say 5 to power 0. Yep, it's 1. So in this particular case, I'm saying 1 times z. Or rather, the z to power 0 becomes 1. So it disappears. Or rather, it's just 20 times 1. So it's 20 times 1 times lambda. So I am left with 20 lambda. There is no z here, so I ignore. I say equals to 0. This will be my first equation. Shall label it equation 1. I proceed to do the same in respect to the other unknown. So this was AZ. I'm moving to AW now. I'm doing dA, dW, meaning I'm differentiating the augmented function with respect to W. So only focusing on where there is a W. So where is there a W right now? There and there. That's where I'm focusing now. Just like I did in the previous part, I begin by taking the power, multiplying by the number in front of the unknown. So I'm still multiplying by the 10. So that will become 5. The z, just like happened previously, it remains exactly as it is. Z to power a half. The w, now it's a half minus 1. Just like before, this now becomes negative a half. There is no w here, I ignore. There is no w here, I ignore. There is a w here, I differentiate. 1 times minus 15 is minus 15. 1 minus 1 becomes w to power 0, which is 1. That is 15 times 1 times lambda. That is 15 lambda equals to 0. That's equation 2. I move on to a lambda. I'm now differentiating the augmented function with respect to the unknown lambda. So once again, only focusing on where there is, only choosing to focus on where there is lambda. That's there, here, and here. So now lambda is occurring 3 times. So that's why I'll focus on as I'm differentiating. So what will happen now? I'll write it again as dA d lambda is equals to, I'll ignore all of this. There is no lambda here. I ignore it. There is a lambda here. This is 1. The power here is 1 times 500. 1 minus 1 is 0. The lambda disappears. I'm left with 500. What about here? The power here is 1 times minus 20 is minus 20. 1 minus 1 is 0. The lambda disappears. So I'm left with 20z. Same scenario here. 1 times minus 15 is minus 15. The lambda turns into a 1. So I'm left with 15. That equals to 0. And that is my third augmented function. Now, if you can take a second to just look at this particular equation, the third equation, you will notice that it looks like whatever we had equated to 0 originally. 500 minus 20z minus 15w is equals to 0. 500 minus 20z minus 15w is equals to 0. So that's just a small tip that when you're differentiating a third equation, each time it normally comes to what you had equated to 0 originally. So at this particular point, we have come up with 3 partially differentiated equations or partially differentiated functions that we need to solve for. Remember what the question was originally asking. Determine the number of units of both commodities that the consumer should buy so as to maximize its utility. We've done 4 steps and differentiated to come up with these 3 functions. But we need to continue to solve for z and w from these 3 equations that we just come up with. And that is what I'm going to show you next. Now I'm going to continue solving the question, but before I do that, I wanted us to make a small observation here. I want us to take a look at the problems that I just shown you initially. In this particular case, we're looking at these 2 questions. Now, how you solve them is exactly the same, but how they have been asked is slightly different. These particular questions the first question that we're solving is straight away asking you to determine the number of units of both commodities that the consumer should buy so as to maximize its utility. However, the second one gives you a utility function as well as your constraint or limitation. But when you look at how it has framed the questions, it's in two parts. It's asking you part 1, using Lagrangian multiplier method, formulate the augmented objective function and find the first order conditions for utility maximization. And the second part is asking you to solve the first order conditions for equilibrium values of Q1 and Q2. How you solve the question is exactly the same, but how it has been set is slightly different. So I just want to make the observation that in this particular case, when they say using Lagrangian multiplier method, formulate the augmented objective function and find the first order conditions for utility maximization, the first order conditions, that's precisely what we've just arrived at in this particular case. In what we're doing, we've solved what we have done here up until step 4. We have solved the part 1 of this particular question. We have formulated the augmented objective function, that is this function that we came up with, and we have solved for the first order conditions for utility maximization. That's the 3 questions that we've come up with. We are now going to proceed to solve the first order conditions for equilibrium values of Q1 and Q2. In this case, solving for the values of Q1 and Q2, but in what we are in the question that we are addressing, determine the number of units of both commodities that the consumer should buy so as to maximize utility. So to determine that number of units, we need to address an equilibrium condition as it has been indicated in this question. So that is something that we need to keep in mind when you're solving for these questions, which is, there's some key things to remember here. That for utility maximization, there is a condition that must be met. So this is something that you should recall, which is essentially a formula that states that the marginal utility of one product divided by the marginal utility of a second product is equals to the price of the first product divided by the price of the second product. So this is essentially something that you should be able to recall when you're solving such questions. So we're going to move on to the next step, applying this utility maximization condition, which is what should happen at equilibrium. Note that this question is stating solve the first order conditions for equilibrium for values of Q1 and Q2. The first order conditions for equilibrium is utility maximization condition, which is, as you can see here, equal to mu1 over mu2 is equals to price 1 over price 2. That is what is happening at equilibrium. So how will that look like when you're solving? We are moving on to the next step, and I shall call that step 5, solve for maximum utility at equilibrium. So we're solving for maximum utility at equilibrium, but exactly what that implies is that, as we've just observed right now, there is a formula that we're required to apply. And what formula is that? The formula is denoted as the marginal utility of the first product divided by the marginal utility of the second product is equals to the price of the first product over the price of the second product. There is an alternative way to represent this particular condition that I've just represented here. And the alternative way to represent it is to simply state it as, that I can restate it as the marginal utility of the first product over its price is equals to the marginal utility of the second product over its price. These two things are similar to each other. However, I shall focus on the first. I shall be focusing on the first one in my solution. So how will that look like? Now it's important to understand what is represented when these variables here that we're mentioning, marginal utility of the first, marginal utility of the second, price of the first, price of the second. What are they when we look at this equation? To understand what they are, we are going to consider the first two equations. That's equation 1 and equation 2. We're going to consider those first two equations in our solution here. Now it's important to understand that what we're referring to as the marginal utility 1, it is precisely this section here. What I am highlighting right now in yellow, that is my marginal utility 1. That is my marginal utility 1, and what I highlight second here, that is my marginal utility 2. So I'll just establish that clearly, that the function 5, the section of the function that I've just identified is 5z power negative a half w power a half. That is marginal utility 1. And the next one, 5z power positive a half w power negative a half, that is marginal utility 2. The prices, if you can take a guess, it is what had been indicated earlier in the question. The price per unit of z is cash links 20 and the price per unit of w is cash links 15. This particular part of the equation. So this represents the prices. That particular section and this. I'll not take into account the lambda, even though I have shaded it, but 20, that is price 1, and 15, that is price 2. So we've just identified our variables there. That is what we're now going to substitute. We're going to substitute these variables into this equation here. So we have our mu1 first of all, that is 5z power negative a half power a half over 5z power positive a half w to power negative a half is equals to 20 over 15. So if you look at this carefully, what we've just come up with is what is being represented here in this particular formula. So in short, we've established the first two equations at equilibrium. Now we're going to continue to solve this particular equation using some algebra that you might be aware of or not. But let us just see what we're going to do here. So first thing I'm going to say we're going to do here is we're going to address the negatives. So when you look at this particular equation, you can see that it doesn't look that friendly with its negative powers, but we can address the negatives. And how do we address the negative functions? There's essentially a rule of indices, which normally tells us that when the powers switch positions or switch, if it's a denominator, make it a numerator. If it's a numerator, make it a denominator. What happens to the powers is that they change their signs, and we want to remove the negative signs from those powers. So that means if we interchange their positions, that means if I move this particular section up, if I move my w up and I move the z down, I'm switching these two things, the w and the z. If I interchange their positions, what will happen is that the signs will also change and they'll become positives. So I can rewrite this as 5. I can rewrite it as 5w. I have moved the w up. Its power turns into a positive, w to power a half, and the other corresponding w there is also to power a half. Down here, what will it look like? 5z power positive a half. I now move the z down. It also changes the sign and becomes positive. A half is equals to 20 over 15. I have addressed the negative signs. I'm going to proceed, still solving this particular question. These are sub steps in just solving this question. I'm going to address the powers by multiplying them. Now, when you're multiplying the powers, another rule of indices tells us that when you're multiplying the powers, you're essentially summing them. So if I'm taking a half times a half for these two powers, what is happening is that I am summing them, the half and the half. So it's essentially a half plus a half. So this will become, my new equation will become 5. Half plus a half becomes 1. No need to write the 1. 5 over 5z, same thing. A half plus a half is now 1. No need to write it. So 5w over 5z equals to 20 over 15. So we have that now. We have simplified what originally looked like a very scary equation, and now we only have 5w over 5z is equals to 20 over 15. So now this is just a simple algebraic equation that we need to solve for. And now, depending on how you'd like to go about it, it's up to you. A low-hanging fruit I can see is just to get rid of the 5s. So here I'll just say that I'm solving. I'll just state that I'm now solving for the unknowns. I think I should actually promote this to actually be a step, because it's actually what we're doing now. We're solving for what the question had originally asked us for. Determine the number of units of both commodities. By solving for the unknowns, we are essentially, yes, we are solving for the value of W and Z. So that means we can make this a major step. I'll say step 6. So step 6, we're now solving for the unknowns. So in this case, as I was noting earlier, that is 5W over 5Z is equals to 20 over 15. I can cancel out the 5's. So I'm left with W over Z is equals to 20 over 15. I can now say that I can choose to make W the subject. So make W the subject here. I will have W is equals to, I multiply both sides by the Z. W is equals to 20 over 15Z. I can label this as a new equation. New equation from where? Remember, I had come up with 1, 2, 3 equations originally. So I can label this as my fourth equation. This is my fourth equation now. Then I'll go ahead and say, in this sub step here, I will say substitute equation 4 into, anyone want to guess into which equation? We've already used the first two equations to solve for the equilibrium. So that means we should substitute into the third equation. That's the one that we've not used. Into equation 3. So that's our next step here. We are taking this third equation that we had. We're taking this third equation. We're going to take that third equation and we substitute in equation 4, what we've just come up with, into this equation 3. So equation 4 is telling us that W is equals to something. So where there is W, I will put this. So I'll write my equation as, no need for this now. I can just rewrite it as 500. I can simply rewrite it as 500 minus 20Z minus 15. Now where there is W, I put this 15 into 20 over 15Z equals to 0. You can see things are looking much better now. I can say that now I am just solving for the value of Z, because now I only have one unknown. We initially had two. Now it's just one unknown. So I'll say solve for the value of Z. Now to solve for the value of Z, I need to open the brackets here first. So we have 500 minus 20Z minus 15 into 20 over 15Z is equals to 0. So you can see here that the 15 and the 15 can cancel. So I have 500 minus 20Z. As I cancel the 15, I shall take into account the signs. This is a minus, this is a plus. So this is a minus times a plus is still a minus. So the 15 cancels. I'm left with minus 20Z is equals to 0. So proceeding to solve, minus 20Z minus 20Z. That will become 500 minus 40Z is equals to 0. Remember, I'm solving for the value of Z. I can move it to the other side. That will be 500. I move this to the other side. When I move it to the other side, it turns into a positive sign. So it's 500 is equals to 40Z. I can solve for the value of Z by dividing both sides by 40. So Z is equals to 500 divided by 40. So what is the value of Z? That is 500 divided by 40. That is 12.5. So the value of Z is 12.5. I can go ahead and call, and then now since I have the value of Z, remember there are two unknowns. I still need to proceed to solve the value of the other unknown, which is the W. Now there are multiple equations that I can choose to substitute the value of Z in to solve for the value of W. Perhaps I can try and find which is the simplest equation to substitute the value of Z to solve for W. If I just scroll up here, you can see there's an instant where I had chosen to make W the subject and I'd called it equation 4. So at this particular juncture, I'd chosen to make W the subject and I had called it equation 4. So I can take that bring it down here, and I can say substitute Z into equation 4. So I have equation 4 there. I'm going to take the Z value, which is 12.5, is equals to 20 over 15 multiplied by 12.5. That is 16.6666. So I can choose to just round it off to 16.7. So eventually we have solved what the question was asking for. It was asking us for determine the number of units of both commodities that the consumer should buy so as to maximize its utility. So our final solution tells us that the consumer should purchase 12.5 units of Z as well as 16.7 units of W in order to maximize his utility. So that's an example of how to solve a consumer utility function. Stick around and I'll solve others as well. But thank you for watching and consider subscribing to the channel.